Good morning, everyone. My name is Rebecca Ashmore, and my thesis is on the concept design of an autonomous underwater vehicle in water battery charging method. To begin with my acknowledgements, I would, of course, love to thank Dean Werner for being my advisor for this thesis. I would also like to thank Professor Martin for being my reader and also helping with the theory. And I would also like to thank the Assistant Dean Harris as my editor for helping me organize my thoughts with thesis. I would also like to thank Brian Keeley for his helpful ANSYS simulations for this. I'll also, of course, like to thank my family and friends for always supporting me. To begin with an outline, I will first talk about the objectives for this thesis, then a brief introduction and background. I will then talk about the basic theory and procedure for this thesis, and then it results in conclusions and then recommendations for future work. I have two main objectives for this thesis. The first is to develop a concept design of a system that transfers energy to an AUV in water without the need for a parent vessel. The second objective is to assess the system by creating and using an analytical design model, determining whether the results are applicable to the use case, and comparing the design model outputs to those in available literature. To begin with an introduction, AUVs are autonomous underwater vehicles, and they primarily charge by swapping out rechargeable batteries. This can take up to about 30% of the mission time, which is a substantial amount. And this is partly due to the current process for AUV charging being first the AUV running low on batteries. The surface vessel and the associated crew then have to get sent out to the AUV, where the AUV is then hoisted onto and off of the surface vessel for recovery, charging, and then redeployment. This is an especially frequent process that has to happen every time the AUV needs to be recharged. Thus, this is expensive, risky, and also time intensive. Some solutions are trying to minimize this problem with both the development of wireless power transfer and submerged docking stations directly connected to shoreside power. But what if you could have a system where a buoy transfers energy in water to an AUV wirelessly? This would completely bypass the need for crewed surface vessels in the AUV charging process. For a general background, AUVs come in different sizes and mission types. These vary their power demands for, usually, their batteries. Lithium-ion batteries are the most common for their high energy densities, allowing AUVs to maximize their payload capacity. To introduce IWPT and HRWPT, IWPT is inductive wireless power transfer, and it has been around for a very long time, widely recognized in transformers before becoming a means to wirelessly charge smartphones. HRWPT is highly resonant wireless power transfer. This technology has been thoroughly patented by a company named Witricity, originally intended to power technology like TVs and other devices in the home. Now it's being commercially used to charge electric vehicles. Two studies that are used to compare and help validate the design model are Pham et al. And Hasaba et al. Pham et al. Simulates various HRWPT coils with different conductivities of the transfer medium, while Hasaba et al. Tests two similar HRWPT coils in seawater. HRWPT is often explained by comparing it to IWPT. Thus, let us discuss IWPT through wireless phone charging. So, this is my phone, which we will call the device. And this is Michael Copy's wireless phone charger, which we will call the source. To charge the device or the receiving coil, power is transferred to it through the fluctuations of the transmitting source coil's magnetic field. These fluctuations cause a reactionary current in the device coil, thus receiving the power to charge its battery. This is the process that you're seeing in the diagram above me, with the bottom coil acting as the source coil with an alternating current passed through it, and the top coil acting as the device, sending out the induced current. The problem with using IWPT is that it is a near field technology. It is very effective over small distances, thus it is tightly coupled. However, if I move the device away from the source, even by a small amount, little to no energy will transfer. The same goes for changing the orientation of the coils. And all of these inefficiencies are happening in air, which completely changes the game when seawater is involved. This is where highly resonant wireless power transfer comes in. HRWPT is a mid to far field technology using a low coupling factor, and namely using the matching capacitors on each side of the circuit to make a highly resonant system, thus the namesake. When in resonance, this technology becomes quite effective for AUV applications in comparison to IWPT. With that in mind, let's go over some of the details. That low coupling and significant resonance is what drives HRWPT's need for high Qs, or quality factors. Designing a high quality factor involves resonant frequency, low resistive losses, and a high self-inductance, which is the amount of opposition met with the current passing through the coil. The main components with influence on those aspects of the power transfer efficiency is the coil and the medium that energy is being transferred in. Those resistive losses are where eddy current losses and conductivity could hold a large weight, notably because the conductivity of seawater is about 4.8 Siemens per meter. Self-inductance is a characteristic of the coil geometry, where a flat planar spiral coil was used. The defining principle to determine the self-inductance is the Biot-Savart law. This is the derivative of the magnetic field depending on the vacuum permeability, current, and the distance of each field length all over the field area. Integrating and simplifying that gives the strength of the magnetic field over the current to get this equation above, which takes a summation of the field at each loop in the coil, building off of the inner coil radius, wire width, and gap between each wire of the loop. Finally, the self-inductance takes that magnetic field and current and multiplies that by the number of turns and the area of the respective coil. Next are the three components of resistive losses: radiative, skin effect, and copper. The most significant of the three are the radiative losses caused by heat loss from eddy currents. These losses depend on the resonant frequency and seawater permeability and conductivity. The skin effect is from the current distribution over the wire surface and depends on the coil length, wire geometry, and copper resistivity. Finally, the copper losses are from the heat loss of the copper, dependent on the coil length and copper conductivity. Generally, the best way to minimize resistive losses would be to use the least amount of wire, a low resonant frequency, and have minimal turns for a small diameter. However, when it comes to seawater conductivity and permeability, these losses are just not entirely avoidable. Now, using these fundamental principles and the many other theoretical details omitted for time, I first needed to define a benchmark of values for the design model outputs to be assessed against. To do this, I created a database of AUVs from the medium to large size range to select a nominal AUV size and endurance. The approximate AUV dimensions were selected to be 2.5 meters in size-defining length, 0.24 meters in width, and about 8 hours of endurance. The endurance is what primarily determines that power demand the system would have to meet, which led to the approximation of 2 kilowatt hours and a 4 to 6 hour charge time without handling. With the HRWPT selected as the system technology, a design model was developed in MATLAB to graphically observe and select various coil characteristics and their effects on coil quality. Those outputs of the design model were compared against the power benchmark and demands to assess if they were realistic and feasible for the AUV application. Then, the graphical results from the simulations of Pham et al. Are observed, and the trends of the curves are compared to the outputs from the design model. Thirdly, the data from Asaba et al.'s test using magnetic resonance with a multi-turn flat spiral coil, which was tested in seawater, is inputted into the design model. This is where the outputs are compared to the measurements from Asaba et al. Finally, using all of this information, a conclusion is reached on whether HRWPT is a feasible for use AUV power transfer method in seawater. So, after doing all of these things, let's first go over the results of the design model outputs. This is the first of 3 generated graphs for the source and device design characteristics. Each curve here is a number of turns and the effect on quality as it varies. The intent here is to then select the number of turns resulting in the highest quality. Thus, 8 turns for the source coil and 15 for the device coil are selected. The second design variable is the resonant frequency. This is a single operating frequency for the system itself, so a median between the 2 peaks are selected. So between 2.5 and 3.9 megahertz, 3 megahertz is selected. The third and final graph for the design model output is for the inner and outer diameters for both the source and device coils. Although it looks a bit more complicated, the higher peaks are for the source coil inner and outer diameters, with the two shorter peaks for the device inner and outer diameters. These were selected to be most ideally 0.17 meters and 0.08 meters for the source coil, and 0.22 meters and 0.14 meters for the device coil. These results from the design model are tabulated here in the top table. These are all the values previously selected from the graphs I described earlier. These coil characteristics, firstly, fit within the 0.24 meter width of the AUV, but are also realistic for the buoy concept system to have. The bottom two tables compare that essential part of the powering requirement. These are all the requirements that are met, with the top table being what the system must be in order to meet those power requirements. The power of 4.33 kilowatts would charge the 2 kilowatt hour rated lithium-ion battery in approximately 0.6 hours, assuming a 30% extra charge time given the decayed rate of charge. This is also in due part of the 0.6 maximum efficiency of this design. Jumping from that to the comparisons from Pham et al. And Hasaba et al., there are 3 graphical comparisons to make to Pham et al. Using the effects of frequency. In all 3, the frequency range of Pham et al. Simulations goes from 0 to 100 megahertz, whereas the design model's range goes from 0 to 16 megahertz. There is also a size difference between the coils being compared, resulting in differences of magnitude. And Pham et al.'s results were also only on their device coil. However, the focus for this first comparison is merely the trends of the curves. The first graphical comparison is of the frequency effects of resistive losses, where you can see the slow exponential growth over a substantial frequency range. The same can be seen in the second graph of the frequency effects on the inductance, with a plateau and then a slow exponential increase across a large frequency range. Finally, the frequency effect on quality was displayed, where you can see the steep initial increase with a slow decrease. The decreasing slope may appear to not as closely resemble the trend from Pham et al. However, this does indeed follow the curve pattern, as the design model output is essentially cut off early in the curve shape, giving the appearance of a different curve. Next is the comparison to Hasaba et al.'s test data. The inputs from their test are shown on the left, using equal coil geometries for their source and device coils, as shown here, with the design model outputs compared to their measurements on the table on the right. Hasaba et al. Did not specify the type of inductance that was measured, thus it was assumed to be self-inductance. Since the design model under-approximated the measured inductance, the associated Q is under-approximated by the same amount, as the resistive losses are within 3% of the measured result. Even with the assumed under-approximation in comparison to the test data, the results of the design model outputs were still of very high qualities. Thus, if the design model was matched to Hasaba et al., the resulting qualities reached extremely high values above the 10,000s. From all of these results, the following conclusions are reached. Firstly, HRWPT, or highly resonant wireless power transfer, is a feasible technology for AUV use. The design model used to represent and assess HRWPT followed the perceived graphical patterns of simulated tests and approximated the limited test data available for HRWPT in seawater. If the system were to transfer renewable energy to charge the AUV, the amount of time required to be extended by the AUV endurance would have to be further observed. The recommendations for future work are that firstly, as test data is very limited in a specific application, testing an HRWPT system in seawater would yield significant helpful results to better understand the efficiencies. Along with this, the next step would then be to make a prototype of the design system, ranging from winding the coils to the buoy system itself. Thank you so much for attending my presentation. Please hold all questions until everyone is finished presenting. I now invite Phoebe Garrett and Lauren Kirk to the podium to present their thesis.